Okay, let's get started. Good morning. Very good to see all of you. This is the kind of last formal lecture we have for the course because next week, of course, you are the ones that will be driving the lecture with your presentations. Are there any questions? Actually, let me put my questions here. So just a reminder that the project papers are due tomorrow at 4 p.m. both on the TED website on the Turn It In sort of assignment and also in my box. Okay. Don't forget that homework is also due tomorrow. You've got sort of double assignments, so hopefully you've had time to work on both of them. But that is, that should be as close to a final draft as possible. You will have a chance to revise once I've graded them next week. But again, because that's based on your score is going to be based partly on what you get on this round, make sure that that final paper is done as much as possible. As I said before, the project presentations should be to me by Monday. So I know I got a couple of panic emails from folks who haven't been in lecture for a while and say, I didn't actually have it ready by today. It doesn't have to be due today. It's due on Monday. So if you're panicked about that anyways, remember that it's Monday that your presentations will be sent to me. Preferably in PDF, PowerPoint. We can do keynotes. I think one of you is doing Prezi. Yeah, I will try. All right. I may ask you to upload it and I'll see if we can run it on the. I don't think there should be a problem. I think the whole point of Prezi is that it's not hard. Okay. But I've never done it before, so it's new for both of us. Okay, and then I've done a revision on the extra credit assignment. So a couple of you mentioned that it's been really hard to get to some of these movies. They've been sold out, and actually they haven't been sold out, but you can't get tickets, and then you show up and there's only 3/4 people there, so it's kind of an odd way of selling tickets. So I've managed to find Woman on the Moon on YouTube, and the library has actually given me the streaming permissions for the movie Contact. So you are allowed to watch these movies on your own and complete the extra credit assignments. They're both due on Monday, actually June 1st, not June 2nd, by Monday at 4 o'clock. Okay? So if you want credit for those, you don't actually have to attend the Contact movie screening, which is actually not happening tomorrow anyway, so you wouldn't need to if you wanted to. So, but you can watch that in streaming. You have to be on the UCSD network to see it, all right, because it's copyright issues and stuff. But look at the turn-in assignment for information how to open that up. Right? I recommend watching it with friends so you can have a discussion about it. That's the whole point of having these events. But you can watch it in the comfort of your pajamas if you want. There will be one more extra credit event next Wednesday, which is the cumulative event for the Cat 3 class that I'm teaching. This is the flyer for it, which doesn't really actually give you any information whatsoever except the list of names. But this is going to be a series of presentations, both sort of formal science presentations, but also kind of artwork, visual performance kind of stuff, all related to this question about are we alone? That's going to be 5 to 8 p.m. Just like the other extra assignments, you have to be there to get credit for this one. And I'll have a sort of a writing prompt for you to actually fill out to get the extra credits up. But that'll be posted probably on Monday or something like that. Okay, but that's going to be Wednesday from 5 to 8 p.m. Small writing down here at Vincent Hall. Yes, ma'am.
I have a question about the papers. You want the hard copy by 4? You guys want before 4?
I would prefer it by 4.
Okay.
Yeah, if possible. I'm gonna revise that because I'm actually not physically here at 4 o'clock. I would like it by the end of the day.
Okay. The
end of the day tomorrow, hard copy. But the turn-in assignment has to be in by 4. That's a hard deadline. So that just made you happy. Okay. All right. Any questions on any of the stuff? Projects, extra credit assignments, life in the universe? Yes, ma'am.
Will we know what day we're presenting?
Excellent question, because I haven't actually told anyone. So I'm going to work up the schedule probably this weekend, and I will post that up in the project sort of folder. I'll have the schedule list, and I'll also email everyone with their dates. All right, it'll either be Tuesday or Thursday, but be prepared for Tuesday, and then feel lucky if you're on Thursday. Question? Yes. Yes.
If we're doing another creative component besides just a presentation of it, does it still have to be a full 10 minutes for us to present
Well, okay, so again, so we did have this choice between doing a creative project and the presentation. The formal presentation part should be a real formal presentation. You should be talking about your work and, like giving slides and talking about the science, stuff like that. The creative project, the presentation is a lot more informal. So you don't have to, for example, prepare any slides if you don't want. You should have your creative project. If it's like a demonstration, you should give some time for doing the demonstration. I know one of you is making a game, so we might want to have 10 minutes playing the game to try it out. But it should be discussion of the whole process, and we can fold in time for questions. If it doesn't go 10 minutes for the creative project, that's okay. Right, I'm not going to be a stickler for it's got to be 9:50 to 10 exactly for that. But I mean, you should talk enough about to give an idea of how you actually came up with the project, the process of that, the resources you used. You should prepare at least that kind of discussion. Then we'll have some time for questions if you go under. But those of you who are doing presentations, please rehearse your presentation. 10 minutes seems like a really long time, but it actually goes by pretty fast. If you have a presentation that has 30 slides, you're not going to do that in 10 minutes. So try to aim for as many slides as minutes as so 10 slides is sort of a good aim, and probably even less than that would be not too bad. Okay. Any other questions? Yeah.
I was just wondering if you're still having office hours today.
I will still be having office hours today. I will probably leave promptly at 1 because we have to set up for the other class project presentations. But I will be in the office, so come on by. 12 a month. Yeah. Yes, ma'am.
I guess on the presentation rubric, you said we have to include attributions, but what if we're presenting our creative projects? How would we include that?
Right. So if you don't have any slides for describing your creative project, you should at least say, this idea came from, Wright et al. 2013, and the idea was from this part of the paper. So you can verbally give it. But certainly in the digital presentations, you should have those attributions actually on the slides. Okay, any other questions? And of course, you should have the attributions in the papers too. Remember using Chicago style. Okay, so today we've got a special guest speaker who is Professor Wright, who's a professor here at UCSD in the physics department, and she's going to be speaking on the Seti project, which I'm going to upload in just a second. Before we start, I just want to give a reminder, a little context of what we're talking about here. All right, we're trying to answer this question of where are the aliens? We've already sort of had a lot of discussion about the sort of quantifying life. This is kind of what we did on Tuesday. Looking at Fermi's paradox and this idea that there seems to be an abundance of possibilities for life in the universe, an abundance of planets, abundance of the kind of conditions that we might expect to be conducive to life, at least based on the conditions that we have here on Earth. And then we've used this Drake equation to sort of come up with some rough numbers of not just how much life is out in the universe, but potentially how much intelligent communicating civilizations that we might come up with. And based on the numbers that we had on Tuesday, we don't know that number within several orders of magnitude, right? So one of you had less than 1, which is bad for us, and then some of you had several million civilizations. And a lot of this is just due on sort of our unknown sort of quantification of some of these really important numbers. All right, fraction of habitable worlds, number of places where life can actually originate. All right, these are all numbers that we don't really know. But even if we don't know these numbers, this is kind of a theoretical approach predicting what you might see. A good experimentalist will say, well, let's just go out and measure it. So Professor Wright is one of these people that goes out and measures these things by actually seeing if we can communicate with aliens. Now let's see if we can communicate with my jump drive on this. Do you want to come up and introduce yourself while I do technical stuff?
Hi, I'm Professor Shelley Wright, and I am an assistant professor here at UCSD in the physics department. I like to build optical and near-infrared instruments. I like to put these instruments and cameras and spectrographs behind big telescopes. I also like to study about galaxy formation and galaxy evolution. But my other field of study is in Seti. I've been part of the Seti Institute for 12 years, and I like to build Seti instruments. So I've built two SETI instruments. One is optical SETI, so I like to search for extraterrestrial intelligence at optical wavelengths. And we just started a new program this year to start the first ever near-infrared SETI search. And so I'll be talking some about that today.
There's a controller right there.
Oh, that's how nice. I'm going to turn out the lights. You know, there's sleepy eyes here. I'm sleeping too. People in the back okay? Can you see okay? All right. So I know in this class we've covered some about the universe for which we live in. We live in the Milky Way. We live in a spiral-like galaxy. I like to always think of it as a Frisbee disk, and we're looking through the Frisbee disk of stars. There's about 100 billion stars in our own Milky Way. Okay? If this is a nearby galaxy analog, it's about 60 million light years away, and it's essentially the same type of spiral galaxy that the Milky Way is in. So the question is, there's 100 billion galaxies in the universe, and then there's 100 billion stars. We're asking the question of, are we alone in the universe? We'll ask this question, are we alone in the galaxy in 1 second? What does this equal? This equals a whole lot of stars. Okay, in fact, it's 10 to the 22 stars. So 1 with 22 zeros at the end of it are the number of stars that are in our observable universe. Okay, that's quite remarkable and should be humbling sitting here on planet Earth that orbits one of that 10 to 22 stars. Okay. So I'm going to go and I'm going to calculate my version of the Drake equation. I'm glad to hear that all of you have calculated your version of the Drake equation. And we're going to play with some numbers here. So I'm going to ask the question, how many civilizations, not just life, I don't mean prokaryotes or eukaryotes or bacterial life, I don't mean dogs, I mean civilizations. So how many civilizations are there in the Milky Way right now? Okay, so I'm going to call this N civilizations. So I have a very simple formula for this. I have the number of stars. This is again in the Milky Way, so we have about 100 billion stars. The fractional of habitable planets, the fraction of those habitable planets where life exists, then the fraction of those planets where life exists that you evolve into a sentient being that likes to develop technology and tools. And then here comes a big one, that the fraction that they exist right now at the same time we do. Okay. So we're going to go through this. So Milky Way, about 200 billion stars. So that's our first value there. Habitable planets, I'm going to give two ranges. Maybe you're going to call me an optimist, but I'm going to say maybe 1% to 10%. Maybe it's much, much lower, but let's just carry this forward. Let's say only 1 in 100 planets, or we have 100 habitable, 1% of the planets are habitable. Then let's say that life is easy. You get a planet for which you think liquid water can exist, and it just becomes a petri dish, and life just happens. Maybe that's not true. We don't know, as Professor Burgasser said. So let's put a factor of 0.1 to 1. So we're going to carry a couple factors forward here. Then we're going to say the fraction of those with civilizations about 1%. Okay. So the fraction of now, let's say civilizations only live for 10 million years. I don't know what happens after 10 million years. Maybe they just like evolve to the next level or next universe. I don't know. Or they kill themselves, or they just go away. But let's say civilizations live for 10 million years. Now this seems incredibly optimistic to me. Let's say they'll live for 10 million years. So the number of civilizations in our galaxy would be 1, with these numbers, in 100 million to 1 in a million of stars existing. Okay. If this is true, then there are 2,000 to 200 civilizations right now in the Milky Way. Interestingly, because if you think of the lifetime of our universe, if only civilizations last 10 million years, there have been 2 to 200 million civilizations before us. So you have to think of, wow, that's kind of cool. There's anthropology of civilizations out there. Okay. So these are kind of optimistic numbers, right? So 2,000 to 200,000 civilizations exist in the Milky Way. I mean, that's kind of cool. I think we're living in a world where we have Star Trek and Star Wars eventually then. Okay, but the key to all of this actually, even these factors, habitable planets, life exists, civilizations, is really the fraction that exists right now. Okay, so the longevity of a civilization, F now, is key to whether we are alone in our galaxy. So let's say that civilizations only last 10,000 years. Okay. We're basically at the cusp of that. So maybe after 10,000 years, an asteroid hits us, climate change happens, we destroy ourselves through wars, a variety of things within this. But that would mean that you would get the number of civilizations be 1 in 100 billion, or 1 in a billion, considering what your fractions are here. Okay. So if civilizations only last 10,000 years, there are still 2 to 200 today in the Milky Way. Okay. You can play around with these fractions all you want, and each of us can play that game and think about what we want to know. What astronomers are trying to answer right now, and astrobiologists, right, are what the fraction of the habitable planets will be. We've learned a lot about other solar systems now. 20 years ago, we only knew of one solar system. We knew of our own. Now we knew of thousands of them. And we know that Earth-sized planets are now common around sun-like stars. I think that's kind of cool. So that kind of, I think, boosts the fraction of habitable planets. Astrobiologists, chemists, biologists try to understand what the fraction of life is. So how do you get habitable life? How do you get life existing to this? So this might change it. And then you have a big jump here for whether their evolution and how common evolution is. Okay, so these are interesting values, and it's always fun to go back and visit the Drake equation and put in your own values and your own perception of what you think the odds are that we are coexisting with another civilization right now in the Milky Way. Koenigke and Morrison was the first published Seti paper. Again, the Seti is Search for Extraterrestrial paper, a search for extraterrestrial intelligence. And they had a great quote that says, the probability of success is difficult to estimate, as we can see, but if we never search, the chance of success is 0. Okay. We don't know. So that's kind of the premise of Seti. So why don't we listen and try to search for extraterrestrial intelligence and communication? So what is Seti? Seti uses scientific methods and rigor to look for communication from alien civilizations. And specifically, astronomers like to use light, or what we call electromagnetic radiation. So this is our great spectrum of the electromagnetic spectrum, where we have radio waves, microwaves, infrared radiation, visible, ultraviolet, X-rays, gamma rays, spanning across all of these different wavelengths here. And so the question is, could they be using some methods for which we use light to communicate? Could other intelligent life be using the same thing? Okay, so this issue of Seti has been around for years and centuries. What I consider one of the first, well, kind of haphazard search was Nikola Tesla. He liked to build large Tesla coils, and he was, of course, interested in developing alternating current and trying to send alternating current and electricity over the air without wires. So that was the purpose of a Tesla coil. He built a huge one of these in Colorado. And here's a large, it kind of looks like a lightning rod, right? You have a lightning rod and a pole here. And Nikola was obsessed with that there were Martians. And he thought Martians would be communicating with us. And in 1899, he announced that he had a signal from Mars from one of his experiments. So there's all these news releases about this. But I think even with one of these first SETI searches, I think we learned an important thing, which is we have to be absolutely certain that our signal is from an extraterrestrial source. So we have to remove any possibility that the source is from terrestrial or a part of our instrumentation, which turned out to be true for Nikola Tesla. So it was later shown that he had a fault in his instrument that gave them these little pulsed signals for which he thought Martians were communicating with him. So it's an important lesson. We have to be careful. One of the first searches was at radio wavelengths. So David Todd was an astronomer, and he too thought Martians would be communicating with us, and they would be communicating with us with radio wavelengths. So he asked the US Navy and all commercial radio stations in 1924 to shut up. Everybody, let's be quiet. Just be quiet and listen. And we'll turn all the astronomical telescopes to Mars and see if they hear a signal. Okay. So here's a telegram asking the Navy, please turn off your stations and turn everything off, which they did comply. So in 1924, they had a radio silence day, and they did one of the first SETI searches. And no, they did not hear from Martians. Okay. So one of the first, I would say, dedicated SETI searches, which is, of course, one of the most famous ones, is Project Ozma in 1960. This is a picture of Frank Drake, who developed the Drake equation, for which we just used in class today. Frank Drake and Carl Sagan began to search in 1960 to look at two solar-like stars, so two sun-like stars, that were in our galactic neighborhood, so actually very close. And the two stars were Epsilon Eridani and Tau Ceti. And they pointed their telescope, their radio telescope, to listen and scan at different frequencies to see if Epsilon Eridani and Tau Ceti were communicating. This was the first groundbreaking dedicated research program to do a SETI search and kind of launched SETI into the future. Since that time, for those 20 years, a variety of telescopes in the US and Russia, all over the world, were used for SETI research. Congress had funded SETI for many years, but in 1988, Congress cut funding. Said the US taxpayer dollars is not going to fund SETI research. This was very upsetting to people like Jill Tarter, Frank Drake, Carl Sagan, and others who had spent a lot of their lifetime looking and trying to figure out ways to best do radio searches for SETI. Carl, inspired by this congressional cut, wrote a book called Contact. And how many people have seen Contact? I just heard that you guys had extra credit if you see it. Oh, wow. It's a good movie. I think it's a good movie. I think it stands the test of time. It has Jodie Foster, it has Matthew McConaughey in one of his first films. And the first half of the film, the premise really is about this congressional cut and not funding SETI research. Jodie Foster is based off a real character. How many people have heard of Jill Tarter? Okay, so Jill Tarter is a scientist. She's now the head of the SETI Institute. She worked with Jodie and Carl to make this film on set. Everything in the movie was true except for them detecting aliens. Okay, I hope I didn't ruin the film, but it's called Contact, so I don't think I'm spoiling it. Okay, it's a good movie. I really enjoy it, so I highly encourage you guys to watch it. So what other SETI researchers have happened? So Jill Tarter at the SETI Institute led one of the major SETI programs called Project Phoenix. It was to look at a bunch of nearby stars here, about 710 stars, all within 150 light years. And they looked at 70 million radio channels. Remember, if you're driving out in the desert and you want some tunes because you're bored, and you go to your radio station and you're flipping through it, you have to scan in frequency to get your radio signal, right? It's like 96.7, 96.8, 96.9. That's similarly to how radio telescopes have to do radio searches. They have to look at a certain particular source, and then they have to scan in frequency space to see if they hear a signal. And that's one of the challenges for radio SETI. So Jill did what was known as a targeted search. So she looked at 710 stars with 150 light years. They really weeded out and said, these are probably the best stars where we think there might be habitable planets. And then they looked at 70 million radio channels to see if that if anybody was talking to us. So it was the most sensitive radio search ever performed. It used the Arecibo telescope, the largest single dish in the world at Puerto Rico. So similarly, there's been other surveys. One's called Serendip. Astronomers like to use Arecibo as well. And they said, oh, we don't care what the astronomers are looking at. We're just going to take some of that radio light and do some SETI research. And so this is part of this survey. But instead of looking at a targeted star, they said, well, let's not worry about what stars to look at. The sky is huge. Let's just let it scan over, and we're just going to get big swaths of the sky. Doesn't matter if there's a star or not, and we're just going to listen to see if there's a signal. So this is performed at the Berkeley SETI Research Center. This spawned what's known as SETI at Home. So SETI at Home is a screensaver. Okay, now here we go. How many people know about SETI at Home or screensavers? Okay. SETI at Home was pretty big in the late 90s and early 2000s. It's very cool. Let me just take a side tangent here. So we had all of this data. And in fact, we had tons and tons and tons of data. And we're looking for very weak, maybe periodic signals. And the SETI researchers realized we have so much data, we don't have enough computing power on Earth to actually do this. We don't have a large enough supercomputer. And people at Space Science Lab, Dan Wertheimer, said, well, yeah, we do have enough computers on planet Earth. They're all sitting at everybody's houses. If you added up all the personal computers that were sitting around the planet, we'd have a very large supercomputer. So they thought about this and they said, well, what happens if when someone's not using their personal computer, they could download our data, process it, and then send it back to us? Brilliant idea. So they generated SETI at Home, and sure enough, they had millions, 8.4 million users, 226 countries, download SETI data, allow their personal computers to crunch it and look for signals, and then send it back to the SETI researchers at Berkeley. And they generated the largest supercomputer by CPU power and processing. In the early 2000s, they had the fastest computer to actually do that processing. The reason why I took the side tangent is because that was such a huge success that we still do this. You can go online. There's things called BOINC. You could say, I want my computer to do DNA sequencing. I want my computer to do cancer research. You can download all sorts of screensavers. So when you're out at a party and your computer is lonely at home, it can be sitting there doing something and processing something. So I think it's very cool that that spawned out of SETI research here. Where next? So the radio SETI community wanted something where they could look at large patches of the sky and look at a lot of frequencies. They got a donation by Paul Allen because we were stuck on private donation money to build a 1 hectare telescope array. This is up towards Mount Lassen in Northern California. There's 350 times 6 meter telescopes was the goal. It's a large field of view on the sky, so this isn't targeted particular stars. And then again, they're scanning in these different frequency ranges. So today, there's only 42 arrays installed. They hit a big pothole, I would say, with the 2008 crash in the economy. And a lot of that money went away in that funding. So they're scrambling for funding right now to complete this project. So if you look at SETI, since Project Ozma, here's Carl Sagan and Frank Drake's first search. Here's Project Ozma here. And you think about the number of simultaneous frequency channels, right? We have to scan in frequency spaces on radio versus year. This is how we've increased. So we're just scaling along with Moore's law. You can see here's Phoenix, Project Phoenix here up at the top. And we've had a variety of different SETI searches that goes along the way. The point of this is that how we search and the quality of our search is totally dictated about present day technology right now. Okay? But it makes sense. We can't do something we can't do. But when we think about how we communicate between satellites, how we communicate with our cell phones, how we communicate versus radio wavelengths on Earth, that dictates how we think about how we would communicate at interstellar distances. So after 50 years, Nobody's phoning us. Should we just call it a day? I like this, to answer that, I like this XKCD comment. So here are two ants talking to each other. We've searched dozens of these floor tiles for several common types of pheromone trails. If there were intelligent life up there, we would have seen its message by now. The world's first ant colony to achieve sentience calls off the search for us. Okay. Right? How we communicate completely dictates how we might search or how we might send a signal. Okay. That's what I love about this cartoon. And if you think about our radio searches that we've done, we barely scratched the surface. I mean, barely, if I could make something smaller than barely. So here is sensitivity on the sky. So how weak of a signal we can detect. Here's the fraction of the sky. So 1 means that all of the sky that we can cover. And here's that frequency space when we're scanning our tuner to look for signals. This is all that we've covered. Okay, just this little region of frequency space. And when we do all sky surveys, we only do at one frequency or a couple frequencies. Jill Tarter says this is equivalently walking to the ocean, taking a pint glass, dipping your pint glass in the ocean, looking in your glass and asking, are there fish in the ocean? And you look in your glass and you say, there are no fish in my glass, therefore there are no fish in the ocean. Okay. Our pint glass is this pint. Our pint glass is what we've searched so far. The galaxy is our ocean. Okay. We have a lot to do. Okay. But why radio wavelengths? This is where my research comes in. So why communicate at radio wavelengths? We do communicate now in many different ways. So in 1961, 1959, Charlestown's invented the laser, okay? Or the maser at that time. He later won the Nobel Prize for this. Charlestown's recently just passed. He was an absolutely brilliant man in many respects. But 2 years after he invented the laser, and just to highlight his brilliance, as well as his care for humanity, he knew when he invented the laser that he revolutionized our technology. And I mean technology and how we use things presently today. But he also knew immediately that this revolutionized many different ways of communication. So 2 years after he invented the laser, he wrote a paper in Nature saying lasers or masers would be the best way to communicate interstellarly among stars or interplanetary between satellites. Okay. Why? If I send out a radio wavelength, I send it out in all directions. Okay, I send it up here, I send it down there, I send it over here, I send it over here. If I'm just trying to communicate to you over there, why would I send that message to Adam and Professor Burgess are right here? I would just send it to you. Why would I waste energy to send signals in all directions? A laser is great for this because I can just beam that signal to the person or the planet or the satellite for which I would like to communicate with. This also means that you get a ton amount of what we call energy per, or information per energy that you can send along that signal. So how would we make a laser beacon for interstellar communication? Charlestown's looked at this in 1961. If we use the largest telescope then in 61, it was a Palomar 200-inch telescope. That's about a 2-hour drive from where we're sitting right here. And we used the most powerful laser at the time. That was at Lawrence Livermore National Labs in the Bay Area. We could outshine our sun by a factor of 3. Okay. This is where you're all supposed to go, whoa.
Whoa.
Yeah, 1961, we could outshine our sun by a factor of 3.
Whoa.
Yes. But even this, our beacon would be visible out to about 0.1 light years. And our nearest stars are Alpha Centauri, around 4 light years away. That's okay, because we're not in 1961 anymore. So let's look at present day. Our current highest power pulse laser is 10 to the 15 watts. Again, you're supposed to go, whoa, 10 to the 15 watts. Like most laser pointers, right, are about like half a milliwatt. Okay. If we use the largest ground-based telescopes, a 10-meter telescope, we can outshine our sun and cross the entire optical bandpass. Red end, blue end, whatever, all the light from the visible light. We can outshine that by a factor of 3,000. So right now, in 2015, we could make a laser with a telescope and send a signal that's about 1,000 light years away and be brighter than our sun. I don't know about you, but that sounds like a really good way to like send a beacon and communicate over interstellar distances. People have come up with all different ways to do this. We could transmit the signal over different planetary zones using whatever n number of stars, get an array of mirrors. There's all sorts of cool things to think about of how we would communicate across interstellar distances. So what I like about optical SETI, or what I'll call laser SETI, it's just a really bright beacon. Okay, so radio SETI, right, we have to search at every particular frequency of light. I have to scan in frequency space. With optical SETI, I don't care. It's like a bonfire, right? If you're on a stranded island in the South Pacific, you're gonna make a fire, right? So you try to beacon people to help you find you. So optical SETI, we're just looking for a burst of light at all visible frequencies. And we're just saying something like, hey, over here. And in that over here, we can send a message. So we do our optical SETI search. We need to do it where those pulses of light that would be sent, or your laser being modulated and sending your signal, needs to be distinguishable, right? We don't want to be Nikola Tesla where we think we're getting Martian signals all the time. So we look at what time frame that would be of interest. And it turns out nanosecond optical signals are very unique. We don't know of anything really terrestrial that can cause this. Lightning storms don't produce nanosecond pulses. We're not aware of most black holes don't produce nanosecond optical pulses. So we don't really have to worry about things terrestrial. We don't have to worry about things in the universe generating signals where we're thinking we're discovering ET. And so what we developed is an optical SETI search that was based on looking for brief nanosecond laser pulse searches. This was first done by Harvard and Berkeley. They looked for nanosecond pulses in the optical band. Paul Horowitz and Dan Wertheimer. Dan Wertheimer, remember, was the gave birth to the SETI at home. And we used very, very fast photomultiplier tubes. This again was in the early 2000s. So we had to wait for technology to be good enough for us to do this. Harvard built a dedicated telescope to do a SETI search. We developed one at Lick Observatory, an optical SETI search. We developed a different system that lowered what we thought were false alarms. We targeted about 5,000 stars, sun-like stars within 100 light years. And then here's Frank. Here's very young me, Dan Wertheimer, and Remington Stone at the time for the Lick Observatory. But this was fun. And since then, there's been a number of optical SETI programs. So the idea about this, here's our alien world. It sends a pulse light. If you use just one detector, you get you would say you get a signal. If you get two detectors, spurious signals can still occasionally happen. So 3 signals arriving at the same time would be incredibly unique. And so this is why we use multiple detectors. Okay, so what I was interested in after optical SETI and doing different optical SETI experiments was really trying to do a different phase space in electromagnetic radiation and trying to probe near-infrared wavelengths. So again, this idea, if I was to send a signal, if I send that signal out to a planet far away, I want to make sure the signal gets there and is very bright. And it turns out that optical wavelengths through the Milky Way, remember when I said at the beginning the Milky Way is like a Frisbee disk? Okay, so if you're sending light through that Frisbee disk where most stars are, and you're sending it through that Frisbee disk, there's actually a lot of gas and dust between stars. And optical light, as it's traveling through space, through the Frisbee disk of the Milky Way, actually gets absorbed by that gas and dust. So it can't travel as far as infrared wavelengths. And this is just seen from this picture. So we're taking a picture through the plane, the Milky Way, through the Prismy disk. And at optical wavelengths here, you notice that it's patchy. If you've been out in a desert and you're camping, or you've been to a dark place, and if you see the Milky Way, you see bright and dark splashes. That's what you're seeing. You're seeing dust and gas that are blotching your view here. If you look at the near infrared, which are slightly longer wavelengths, it's completely transparent. So you get rid of all that gas and dust, and you can see all that light from all of the stars here. So if you're going to send a signal, and you're going to send a laser signal, you know, why we really want to do this at infrared wavelengths, not optical wavelengths. But the problem was we didn't have good enough detectors and technology to do this 10 years ago. We had to wait for them to become good enough. And they have. And the reason why we can do this now is because of your cell phones, because of the telecommunication industry, laser range finding, and then missile detection. So this is just showing a cartoon of, we have different missiles and surveillance going up there. And what they want is very fast response infrared detectors, the military does, to be able to track missiles and other devices. So because we had good detectors, we were able to then start near infrared SETI. And so our group developed new detectors with, there are only 2 companies in the world at this time that make these type of detectors. They use near infrared detectors, and they look at very fast pulses. So here's one detector. Remember, I have 2 detectors. I have a pulse signal here. This would be like, hooray, we have ET. We have another signal here. You'd say, oh, there's not one here, so probably not ET. So we've developed a new near infrared SETI experiment. We just commissioned this at Lick Observatory just in March. So our goal is to target thousands of stars at much larger distances. So the majority of radio searches have been looking at stars that are all within about 100 to 200 light years away from us. But if we have infrared SETI, we can then transmit over much larger distances. So we're going to look at larger, about 1,000 to 2,000 light years away from us at stars. We're going to also look at other phenomena like black holes and neutron stars. And here's our team commissioning this in March. So we were quite excited about this. This is the first near-infrared SETI search ever underway. We're kind of carving out new space and learning a lot about these new detectors. The exciting thing about this is that, you know, I keep getting back to this. How we communicate or how we do our search is really dictated about our present day technology. And so I really think we need to stay abreast with how technology develops and how we do communication to do better SETI searches. So what's next with SETI? We have radio SETI here, which dominated the last 50 years. I talked a little bit about optical visible light SETI with lasers, now infrared SETI using lasers. But you can see that we have, maybe they're communicating over different frequencies or different modes of light that we haven't looked for. But ultimately, we're kind of resource limited. We need more people, we need more funding to actually carry out these SETI searches. So here's a couple fun ideas. Gravitational lensing SETI. So you can send out a big space probe about 550 AU out. Use the fact that of general relativity, that light rays bend with space and time, and you look at a signal, and the signal gets sent. Our sun sitting in that gravitational well, it bends the light rays to it and focuses it down to our space probe and makes it incredibly sensitive. That's just a fun idea. This is one of Frank Drake's happy ideas to do for SETI. Neutrino SETI, I think this is one of my favorites. Maybe they're not even using light. Maybe they're communicating via other particles. Neutrinos are great. They're inert. They're neutral. They're transmissive. They go everywhere. They go stream through us right now through the universe. That would be a very good way to communicate. You'd have to be very advanced to know how to detect neutrinos. So maybe there's a big chatterbox of people communicating over like the neutrino internet of our galaxy right now. We just don't know it because we haven't gotten there with our technology yet. So people have thought about how to do neutrino SETI searches with different neutrino detectors here. So all of this, as I said, is dictated by the technology we have, dictated by the number of people we have, and the resources and telescopes. So getting back to the fact that Congress cut SETI in 1988, more recently, the Congress has realized that this may be a national security hazard if we're actually not doing SETI searches, or if other nations detect SETI before we do. In that mind, the House Committee on Sciences and Space Technologies met last year in 2014. They called forward Frank Drake and Dan Horkheimer and some other SETI researchers and said, hey, what's going on? What are you guys up to? What's, how likely would it be that we get life in this? There was a space.com article. People said, we'll find alien life in this lifetime. The scientists tell Congress, that was the title of the article. The point from this is that there's lots of interest in SETI. Okay, everybody loves this topic. Okay, everybody loves to talk about SETI. Everybody loves to talk about life in the universe. I think this is why all of you are sitting in this room right now. It's a very deep philosophical question. It's a very interesting scientific question, how we would communicate across interstellar distances. But we have no funding. We do this all by private dollars. Okay, there's other countries that are now trying to do this as well. So the thing I will say the most is that we need more people. If I have my little message, I am kind of shocked that one of the most profound questions in science has little funding for it. Okay, so for me, I think our greatest minds should be thinking about SETI, new ways, methods, technologies. How would we do a search creatively? In this report to the House of Committees of the Congress, there's, quote, there are about 24 scientists on the entire planet that conduct SETI observations. Wow. Okay. That's not very many.
Wow.
Yeah, thanks. So that's like current, in a brush stroke of the current state of SETI. And I'll take times for questions and turn on the lights here. So let me end there. Yeah.
Questions for Professor Wright?
Yeah.
So if you guys had funding and there's more scientists, do you believe that we would be able to find life in the universe in our lifetime?
I think there's a good chance, actually. If you asked me that even 5 or 10 years ago, my answer may be different, and even 5 years from now. But everything that is, I think astronomy is under a big revolution, at least with their understanding of how common planets are and how common Earth-sized planets are. The fact that those are common, I think, bodes well to this. We need to, as I said, we just did a pint glass of the ocean. We have the resources to do a very complete SETI search. We just haven't done it. Okay, that's also part of this. We have the technologies to communicate. We also have the technologies to receive. And interestingly, there are a lot of other countries right now that are, pursuing trying to do more in-depth SETI research in the coming decade. Yeah.
I was curious when we talked about the background radiation noise from the Big Bang or whatnot. Have you thought about that maybe just talking to us? Because neutrinos that split that thought.
No, I haven't. I have never thought about the cosmic microwave background. That's because it's really uniform across the plane of the sky. And so the CMB is very interesting because it's what we call homogeneous and isotropic. So every direction we look in the universe, it's the same, coming from that same direction. So, but that would be a big, interesting wrench in our cosmology. Yeah. All right, well, I have a question for you guys. Do you think that I want to know, do you think my calculation for end civilizations was optimistic or pessimistic? Or what do you think? Let's go all the way back here. Let's go to this way. Okay, raise your hands if you think this is really optimistic. Yeah, okay. Oh, good. It's probably like 2/3 of the class. All right. Do you think this is probably more likely then? Or is this even still too optimistic?
I think it's a lot.
Still optimistic.
I'm a pessimist.
You're a pessimist? And you guys talked about Fermi paradox?
Mhm.
Yeah. Okay.
Okay, well, I don't know, are you gonna stick around a little bit, or you wanna?
I am probably going to go.
Okay. Well, if anyone has any last questions, this is your rare opportunity to ask a question of someone who is looking for life in the universe actively. So, anything else? Okay, well, let's thank Professor Wright. Thank you. Okay, so the second, so sort of as we end up this class, I want to talk a little bit about not just listening. So a lot of what Professor Wright is doing is hoping that there is a signal that comes to us and that we can actually pick it up, which is, we're banking on two things. One, that we have the capability of detecting signal, and that's why she was talking a lot about the technology development. Are we ready to actually see the signal? Of course, we also have to get a signal sent to us. Now, that's a one-way form of communication. We've been using our technology not just to receive signals, but also to send signals out over the last, actually, couple hundred years. Professor Wright talked about this facility, the Arecibo Observatory in Puerto Rico. Back in 1974, which I know none of you were alive in because that's when I was born, she mentioned Frank Drake and Carl Sagan, and these two scientists got together and devised a message to send, not just to receive, but also to send out into the stars. And this is the message in color-coded form. In fact, what was really sent was just digital numbers, right? Ones and zeros. But if I just make the ones bright and the zeros dark, and you reformat this image into a 37 by 73 pixel 2D picture, this is what you would, if you did that, this is what you would see. And there's all sorts of information encoded here pictographically. We have a sort of numbering system in 1 to 10 in binary. This is a sort of binary counting of the atomic numbers of those elements that are so important to life, right? HCNOP, got sulfur, that's okay. These are models for nucleotide sugars. This is obviously a picture of DNA. Here we are, a little picture of people, the best you can do in binary code. Here's a little model of the solar system with one particular planet indicated. And this is a picture of Arecibo, again, in this digital format. So this was a signal that was broadcast out by this Arecibo telescope. It was sent out to a globular cluster in the hopes that, so globular clusters are massive collections of stars, something like 10,000, 100,000 stars in one sort of massive cluster. The idea is pointing at a place where there's lots of stars, and maybe there's lots of planets, and maybe there's some alien life forms up there. This message is still on its way, by the way. It will take about 10,000 years to get there. So when it passes our lifetime, whether we know it got received or anything like that. But this was an attempt to actually, instead of being a passive listener, to actually be an active communicator. This is not a new idea. Even before the advent of radio technology, people have been thinking about this. Many of you may know the name of Gauss from Gaussian functions and Gauss's law in physics. But Gauss also thought in the 19th century about aliens, as did many 19th century scientists. And one of his ideas that, again, this is before Maxwell had discovered sort of electromagnetic radiation and radio waves had actually come into existence. His idea was, let's just make big pictures on the Earth, and hopefully aliens will see them and realize that we're really smart. So he actually proposed, he and another scientist named Littrow proposed drawing something like a Pythagorean square somewhere in Siberia, and laying out lots of logs and trees and stuff like that, and making this humongous picture. Because if someone looked at the Earth, maybe they would see that, hey, this doesn't look natural and it looks mathematical. Maybe these are intelligent beings on this planet. Pretty crazy idea. Although in fact we have evidence that even before this, back in the sort of more early civilizations, also had these very odd drawings on the ground. This is the Nazca geoglyphs. Geoglyphs means earth writing. So we have these sort of pictographs that are sort of dug into the earth from these ancient civilizations. Nobody knows why they're there, right? Sort of like standard idea is that they were sort of drawing these things for their gods, which are up. But of course, a lot of sort of alien enthusiasts believe that these were communicating with alien life forms, ancient astronauts at the time. Who knows? But they're, it's kind of the same idea, drawing things on the ground to communicate sort of big ideas out into the space or upper regions. You probably know something like this in terms of crop circles. Crop circles have actually been around since the 17th century. There's these news articles of the sort of the mowing devil who is creating patterns in crops. Certainly, this is sort of a picture not of aliens coming down and landing, but probably just many hundred years of playing tricks on farmers. All right, this is actually a purposeful one that's done by an artist. But this whole idea that we could signal without actually sending radio waves is not an old idea, and it's again thinking about in terms of how could we communicate with another life form, whether those life forms are gods or actually aliens. There's other ways we can signal other life forms without using radio waves. We have this issue with global warming, that the global temperatures are going up, and one possible solution to that is just to decrease how much sunlight we get. So there's these ideas of maybe sending up essentially blinds in orbit around the sun, and so that they can block out some of the sunlight. You can imagine having something that has little louvers, so you can close them as it gets too hot and then open up when it gets too cold, right? Having sort of like thermostat for the Earth. But you could also presumably use this to kind of make signals, right? So you could, sort of send mathematical signals by just sort of occasionally opening and closing these things. These, again, might be something that could be seen out in the universe because you're changing the light of the sun in some sort of seemingly artificial way. That might be something that not only we could communicate with, but maybe we would see these signals in the transits of stars as well. But so these are all ways of communicating on space, and they're in some way, again, passive messages, right? We send these out either as a drawing, or we send them out as a radio signal, or we make this pattern that gets transmitted out into space, and we have no idea if anyone's listening to it. So another thing we could do is maybe actually just send stuff out in space. Again, back in the 1970s, a pair of spacecraft called the Pioneer spacecraft was sent out in space. This is the basis of the project we did yesterday in our discussion lab. One of the ideas is if we're sending this thing off into the outer part of the solar system, and eventually it's going to make its way out of the solar system, well, let's attach something to it so if someone somewhere in the future picks it up, we can have some kind of message there. So these are the Pioneer plaques that were attached to the spacecraft. 6 by 9 inches, so only about that big. That was sort of the constraint for our drawings yesterday in discussion. But the idea is that, hopefully this is one way of sending a message out in a bottle. We did the same thing with the Voyager spacecraft in the late 1970s. This object here, the Golden Record, was attached to it. You can actually listen to the contents of the Golden Record on YouTube.
Then adaka suara ini saya tembam ikan yang saya katari apa nakong.
I wish to extend greetings and friendly wishes to all who may encounter this Voyager and receive this message.
Enviar a todos los seres del universo un afectuoso mensaje de paz y felicidad. Que el futuro nos depare la oportunidad.
Ook België stuurt zijn groeten de ruimte in aan boord van de Voyager. En hoopt dat deze boodschap als ook...
And good luck, Pandisiwana Depan. Salon, a member of the Committee on Outer Space, and we believe...
So there's 5 hours of this. I'm not going to play all of it. But again, the idea is that sending a message out in the bottle with these spacecraft that we're already sending out anyways to explore our solar system, it's going to end up outside the solar system. In fact, we now know that Voyager 2 has passed through this sort of transition between from the magnetosphere of our sun, the very large magnetic sort of sphere that covers our entire solar system. These spacecraft are now starting to plow through that and are into interstellar space. So we are really starting to send objects out of our solar system, except going really slowly, right? This thing's actually moving quite fast, but it's going to take 100,000 years to get to the nearest star. So this is kind of a long shot, and it's a long investment. But again, it's another way of sort of communicating out there, at least in terms of a long-term message. Now, so all these things that happen. Yeah, go ahead.
Is the record continuously playing, or is it?
Oh no, so it's not. It's not. If it's playing in space, you don't hear any sound, so it's kind of not useful. It would use up the battery. No, there's instructions on how to. You can kind of see that here. This little part here is instructions here and here, instructions how to actually build a device to play this record. Now, if I were to receive this and this was my only instructions, kind of like IKEA instructions, I'm not sure I'd actually be able to build it, but the hope is that an advanced civilization would kind of figure out, or little scribbles and figure out what to do with this thing. We notice the scratches and the patterns and know what to do with it. And by the way, this may not even last 100,000 years, right? 100,000 years is a long time to be in space. There's cosmic rays in space. There's all sorts of high energy radiation. It's likely that this spacecraft will probably deteriorate well before it comes within the nearest stars. But it's a shot, so who knows? Now, so these kind of things have been going on for the last 40, 50 years. The question, of course, is whether or not we should really be doing this. And this actually was the topic of a recent New York Times article just at the beginning of this quarter. I actually mentioned this at the very beginning of the quarter. Should we be actually communicating? Should we actually be shouting out into the cosmos? You know, are we really ready to find aliens who may be more advanced than us and may have not, the best interests in mind for us? Stephen Hawking, who's a very famous physicist, is the physicist that's in a wheelchair, commented on this himself. He said, if aliens visited us, the outcome would be much as when Columbus landed in America, which didn't turn out so well for the native North Americans. So we have to be very careful about getting in contact with advanced civilizations. Carl Sagan, who we've been mentioned a couple times today, who was a real advocate for searching for extraterrestrial life and thinking about extraterrestrial life, was also very shy about the idea of actually actively communicating out with life. So this is a quote that's widely attributed to him, that the newest children, that's us, in a strange and uncertain cosmos should listen quietly for a long time, patiently learning about the universe and comparing notes, before shouting into an unknown jungle that we do not understand. So a very conservative perspective that SETI is okay, but messaging, which is now known as METI, messaging extraterrestrial intelligence, we may not be ready to do something like that. But the thing is, we're doing it all the time, right? We're sending out radio waves, TV signals, cell phone signals out into space continuously. We've been doing it for 100 years. So whether or not we intentionally communicate with alien civilizations, if they have the right technology, they probably know we're already here if they're within say 50 light years of the Earth. Right. So all these things are, again, ways that we could kind of answer the question, are we alone? Is actually seeing if we can hear any communications from outer space, or actually making contact directly through these sort of various messaging methods. But Professor Wright brought up a really important point. If civilizations don't last very long, we don't know how long civilizations last because we've got one global civilization that we have a model of, and fortunately it hasn't ended yet, so we don't know the answer to that number. But if it's a short period of time, it may be that there's really very few alien civilizations out there today that we could actively communicate with, or at least send messages back and forth. And so maybe one thing that we should think about is how do we maybe look for evidence of prior civilizations that existed for long periods of time, but maybe have died out or wiped out in some way. So this is the Astro Archaeology that she kind of referred to. And to do that, we have to go out into space, all right? So it's very fun concept. Let's just go out there. Let's go travel into the stars and see what's out there and visit different worlds and see if we can find these civilizations. And of course, we have the technology to go out into space. We've had an active space program for 50 years. All right, remember the space shuttle? Here's a really beautiful picture of the launch of that. We've been to other worlds, at least the moon. All right, we've had 12 people visit the moon in the course of the Apollo space program. But going out into deeper space is a whole other question. All right, and so again, I mentioned Voyager, in the sort of almost 40 years Voyager 1 has been moving. It's traveled 20 billion kilometers. It is the farthest object that we've ever sent, right? So the object has traveled the most distance. It's also the fastest man-made object that's moving out in space. But even with all that, it will still take at least 100,000 and maybe up to 1 million years to reach any of the nearest star systems. And that's only if it's pointed at a nearby star system. It's actually not pointed at any of the stars. It's just flying out. So likely this will never intercept any other planetary systems at all. So not great, right? This is a very slow process. So interstellar travel is not something that's immediate like SETI or sending a signal. So if we actually go out into interstellar space, we have to think long-term, really long-term ideas about how we would do this. So some ideas that have been played out in sort of science fiction and literature, you can have generational ships. So you put a bunch of people on a ship and you plan for them to be on that ship for not just their lifetimes, but many, many lifetimes. And so there's all sorts of stories where this played out. Probably the funnest one is, in Wall-E, there's this generational spaceship that's got all of humanity because we've trashed the planet. And then we've sent a little robot to fix everything. One tiny little robot to clean everything up. But this is an idea that's been played out in how you would actually send physical human beings around into space. Because of the large distances involved, you have to kind of keep them going in this little bubble for many, many generations. We could put people into stasis or sleeper ships. All right, this is a theme that's sort of seen in a lot of Star Trek movies. But it's also a theme that we play here on Earth because there are these cryonic sort of centers that if you're very wealthy and you die and you want to be revived sometime in the distant future when our medical science is advanced, you could have your body or even just your head frozen with the hope that you'll be resuscitated sometime in the very distant future. People have paid big money to be frozen, which is essentially the same technology that we talk about if we want to send people out into space, all right, for long periods of travel. So this is science fiction, but there's also a little science actual happening going on. I'm not actually sure how scientific this is because nobody knows if they'll be revived, but people are betting on it. Now, another even cheaper option is not to send bodies because that's the whole problem. Our bodies only have a limited time span, right? At most 100 years. And it's going to take a lot longer than that to get to the nearest stars. So don't send the bodies, just send the eggs and the sperm, right? So there's other ideas of sending seed ships that literally carry the genetic material that might raise a whole group of human beings and maybe even all the plants and animals and everything else. And we have a sufficiently intelligent artificial intelligence or robotic system. Perhaps you could breed an entire ecosystem by finding a habitable planet and then just planting it there. Right? Now this has all sorts of ethical issues. What if there's already a life sort of life biosphere on that planet? Would we be wiping out that biosphere by invading it like a virus? And what if the ship gets to another planet in 1 million years and the human race has been wiped off our planet? So now we've somehow temporarily transported our species to another place, even though our original species doesn't exist. All sorts of great science fiction and sort of the different scenarios that can arise from these different ideas. The whole idea is that this takes time. Time is one of the big barriers to whether or not we can really go out and colonize the universe. Now, another issue is whether we actually have the capability. So I'm going to do a quick question here. So let's see. How far have humans traveled from the surface of the Earth in your lifetime? There's 5 choices here, right? And just to scale, this is where they are. So here's the Earth. A is just near Earth orbit. B is just a little bit further out. C is in where we have our geosynchronous satellites. There's the moon and going past the moon. Get your cards out. Anybody need an extra one?
No, I was just having a question.
Okay, yeah.
You mean in our lifetime or by
How far have you traveled in your lifetime? And actually in the lifetime of everybody in this room. How far have we been off the face of the Earth?
So it doesn't include stuff that happened before we were born.
Yeah, in your lifetime. In our lifetimes. Where have we been? There's an extra form in the back. Yeah. Yes, ma'am. Yeah, human beings. How far have human beings been in all of our lifetimes? All right, count of 3. 1, 2, 3. Okay, actually, most of you have chosen. Is that E? Yeah. Okay. Good. Okay. So most of you have chosen the same answer, which isn't E. It's. Yeah, most of you chosen the same answer, which is D. Okay, so D, about the distance of the moon, 60 Earth radii. None of you chose the correct answer. A. In all of our lifetimes, including my lifetime, and I'm a bit older than you, that's as far as humans have been off the face of the planet. Near Earth orbit. All right, this is where the space shuttle, this is where the space station, this is where any of the Russian spacecraft can go. We have been no further than that in 40 years. In at least 40 years. Done 40. Yeah.
When was the last Apollo program? Because I thought they had a couple of them.
1972 was the last time we were on the moon. Last person on the moon, 1972. Since that time, we've been there's the moon. So since that time, we've been right there and no further. All right, now there's been lots of things that we have not been doing in the last, at least in your lifetime, and even my lifetime. So we used to travel to the moon. We don't do that anymore. We used to fly the space shuttle. We don't do that anymore, right? The space shuttle program was stopped in 2011. I could also, when I was younger, buy a ticket to go to Paris in 2 hours from New York on a supersonic jet. Can't do that anymore either. So we have a lot of optimism about the idea that we could build these kind of spaceships, and science fiction has beautifully humongous, tremendous star destroyers and Death Stars and stuff like that. The reality is that this depends on funding, and this depends on commitment to actually doing these kind of things. So Dr. Wright talked about the funding for Seti being dropped off. This is the funding for the NASA program from 1962 to 2014 as a fraction of our national budget. And you can see going to the moon was pretty expensive, right? The Apollo program took up something like up to 5% of our national budget. But now we're at about 0.5%. And this covers almost all of the sort of space activities that we do off the Earth, 0.5% of our national budget. So that's one issue, is that it's going to cost money to go and do these kind of things. Even if we want to travel in our own solar system, going to Mars is an expensive expedition. Right? Many estimates give it about something $80 to $100 billion. Now, to keep that in perspective, that's something like $1 a month for every American, and that's it. That's how expensive space is, $1 a month. So, like a coffee a month would actually send us into Mars. So when you're thinking about the cost, you have to keep in perspective is that there's lots of money to go around. It's just what are we deciding to do with it? Is the best thing to do is go to space? Is the best thing to do is make sure we have food and security? These are all sort of the things that we decide as citizens. There's also physical difficulties in this. If we want to actually travel into interstellar space, we have to get much better engines. And more importantly, we need to use a lot of energy. In order to go to the nearest star, we'd essentially have to consume all of our civilization's entire energy budget up until this point to do one trip. All of the energy we've used up until this point in time of our civilization, we have to put into going to one trip. Energy is really a big problem. This is some examples of how much energy you would need just to do some of these different trips. This is measured in how much antimatter fuel, the most efficient source of energy would be to create antimatter particles and collide them with particles and extract all of that mass energy in one go. If we could do that, we would need, for every kilogram of cargo or spacecraft, 38 kilograms just to go to Alpha Centauri, the nearest star. This is with an invented engine that doesn't exist and a 40-to-1 fuel to mass ratio, which we don't do today with rockets because that's way too much. Energy is a huge deal. But we do use more energy over time. This is a plot from Professor Murphy here at UCSD, who's looked at energy usage and sort of projections in the future. This is how much energy usage in the United States there has been since 1650, right? So this is 350 years worth of data. And it's plotted on a log scale on the axis here. And what you can see is that there seems to be this fairly nice linear relation in how much energy we use in our country over time. Now, part of this is new technology. Part of this is just more people using more energy. But there seems to be a fair, what we call an exponential growth in the amount of energy that we use over time. And that's something like 3% growth rate, right? If you have interest rate, this is like 3% interest return on your money. This is 3% more energy used over time. If we project that out into the future, so here's today. Right now we use something like 10 to the 4 times 10 to the 12 terawatts of energy, 4 times 10 to the 12 watts, but like 14 terawatts of energy as a world. If we go about the same sort of progression in energy usage, in about 400 years, we'll have used all of the energy that arrives from the sun on our planet. So that would be building solar cells that cover our entire planet. We'd be at that much energy usage, which is a pretty limiting factor. But if we go past that in about, something like 1,400 years, in order to stay on the same track, we'd have to use all of the energy emitted by the sun. We'd have to collect every single light photon coming from the sun. That would power our civilization. If we go 2,000 years in the future, we'd have to collect all sources of energy in the entire galaxy to keep going. And it's at this point that interstellar travel becomes feasible. So there's some real issues here with this, right? And there's another big problem is that when we use energy, we create heat waste. And if we actually project that same time and figure out what the temperature of the planet would be from all the heat waste, in about 300 years, it starts increasing the temperature of the planet. In about 600 years, actually, in about 500 years, it gets hot enough for paper just to spontaneously burn, just on the surface of the planet. So we can't do this on the surface of the planet. If we really want to create this much energy, we actually have to get off planet in order to do this. So these are some of the limitations. And I should also say, I mentioned earlier when Professor Wright asked, are these numbers, pessimistic, optimistic? And I said, I'm a pessimist. When you actually look at the energy usage in the US, it's actually started to decline a little bit. And in fact, if you can actually grab this data from the World Bank, in the last 10 years, our energy usage per person, at least in this country, has declined for the first time in about 300 or 400 years. So we may have actually kind of gotten to the point where we may not be able to go much further on our energy scales, at least here on the planet. And so any kind of future that we have to do these kind of things will require a really deep thought about how we actually get energy and what we do with that energy and what we do with our resources. So, I don't want to leave on a super pessimistic perspective, but if we really want to become not just people who listen to potential aliens, but we actually go out there and explore, we have to solve some really major problems here on our planet and our civilization, how we use resources, because these are not something that we can just hop in a rocket ship and go. We actually have to think deeply about how we would do it. Okay, any questions? Yes, sir.
On the slide with the energy usage, for like next 2,000 years.
Yeah.
What were the green?
So this is if we go back in time. So the Industrial Revolution happened about 150 years ago. So when we talk about the time in which we have to use all the energy from the sun, that's the equivalent of thinking back in history to the Dark Ages. Not that long ago on a human history scale, but that's where we would be heading if we actually stay on that line. It's not long in the future.
Well, for us.
For us as individuals, yes, but not as a human civilization. Okay, all right, so reminder that papers due on Friday, homework's due on Friday, presentations are due on Monday, and we'll start doing presentations on Tuesday in lecture. Tatiana? Yes.
I was trying to use a simulator and I don't know how to find these two columns of dollars. Because it said it would be on PowerPoint, but I skimmed them all and I couldn't find how to find them.
Should be on the PowerPoint. Let me make sure.
Maybe I just didn't know what lecture it was on though.
That would be the lecture on finding exoplanets. Let me just really quickly look so I make sure that I'm not.
It's still annoying for an application to take more than a couple seconds.
Right, I looked at the